All right, so grade 11 chemistry, we're talking about gas laws today. This is what's on the docket. First, we'll talk about the particle theory of matter and gases in general. You guys should be pretty familiar with that. Then we'll talk about, start talking about dead white guys. So Boyle, Charles, and Gay-Lussac. But these guys just have laws named after them. So Boyle's law is pressure-volume relationship. Charles' law is temperature-volume relationship. We have to take a little detour and explain absolute zero along the way. Gay-Lussac's law is temperature and pressure, and then we're going to combine those gas laws and kind of synthesize some new stuff with them. So this is where we're going to be able to do a little bit of mathematical problem solving with our gases. So let's just jump right into it. We're talking about the particle theory of matter and the gas state. The particle theory of matter says all matter is made of particles. All particles are pure substance, are identical. It's like, water is water is water is water. All particles have space between them, and all particles are always moving. And then all particles are slightly attracted to each other in some way. Well, we care about those middle two. All particles have space between them. All particles are always moving. A gas really exemplifies this. There's lots of space between the particles, and they're moving really, really fast. Right? So that's a gas. I'll bring this over to the left here. There we go. That's a gas. Right? Space between the particles. And they're moving. Gases typically have very low intramolecular forces. They're usually quite small and usually quite nonpolar. So you see methane's a gas, ethane's a gas, propane's a gas, butane's a gas, but you get to pentane, it's a liquid. Properties of gases, there's a distinct set of properties here. Gases are compressible. You can compress a gas. It's very hard to compress a liquid, but it's easy enough to compress a gas. Number two, the gases will increase in volume a lot as temperature increases and vice versa. So, changing volume. Number three, gases have low viscosity and low density. So low viscosity means it's easy to move your hand through them and stuff like that. There's not a lot of resistance to flow. And low density because of this, right? Because they're all over they're flying all over the place. So very low density compared to liquids and solids. The last piece is that all gases are miscible. So they can mix in any proportion. You can have 80% nitrogen, 20% oxygen, 20% nitrogen, 80% oxygen. All of this follows directly from this theory that we call the kinetic theory of gases, which has already been explained. But this is kind of a better way to explain it. It's kind of an extension. It says that a gas is a large number of particles in constant random motion, and they collide with each other and the walls of the container that they occupy. So the collisions are pressure. That's what pressure is. Pressure is just the collisions. And that's why increasing the temperature will increase the average speed and their energy. So, this is where a lot of our gas laws are just going to come from. They're going to come directly from this kinetic theory of gases. Here's some animations of gases doing their thing. The left one is a simpler one. You can see that there's particles, they're flying all over the place. Sometimes some of the particles are moving fast, some of them are moving slow, but on average they're all moving, some average speed. And the same thing's happening here with a bit more of it, and you can see the trails that some of the particles, 5 of the particles have trails, and you can see these random walks that they go on. And sometimes they're moving fast, sometimes slow, so this arrow on this particle is tracking its speed at any given time. So you see sometimes it's moving fast, sometimes slow, but on average they move at a certain speed. So that's how you can think of a gas. It's just a bunch of things moving all over the place. And the hotter it is, the faster they move on average. And collisions with the walls of the container, that's the pressure on the container. That's what we're going to get to. Now there's some assumptions in this theory. The assumptions, there's 2 of them. The first one is that the gas particles are point masses. They take up no space, right? If in order for this theory to perfectly explain gases, they should take up no space at all. But of course, they do actually take up some space. A real gas, the particles themselves, the atoms, they're very small, but they're there. as an example, I've mentioned before, this room has about 50 pounds of air in it, right? So take 50 pounds, something that big. If I took all of the air in the room and I squished it together into something solid or liquid, it would be, it would be big, but it wouldn't be nearly as big as the room. But it is a reasonable amount of space. And then the other one is that gas particles do not attract or repel each other. They do attract each other very slightly. There are some intermolecular forces. That's why we can turn gases into liquids, like liquid nitrogen and stuff like that. But at room temperature, it's pretty much a non-factor. They're moving very, very quickly. So it's a good enough model. It's not quite accurate, but it's good enough for the behavior of gases in common conditions. We can make predictions, and that's all we want from our models. All right, so now we're going to get into our gas laws, and this is our first gas law. I'm going to pause and set up my stuff. So this is the first gas law we're going to talk about. These are all named after dead white guys. They were kind of working together, and each one kind of discovered a different gas law. But with the molecular theory, with this theory, the kinetic theory of gases, you can actually predict the law yourself, now that you know that the kinetic theory exists. So let's assume we have the same temperature in our container and the same number of moles of gas, and we change the volume. Right, if I change the volume. So let's say, for example, here we go. I'm going to take this balloon. I'm going to fill it up with some air. And if I trap it, if I trap it like that, now there's the same amount of moles of gas in that balloon, and it's going to be at the same temperature. So we're keeping those constant. I'm going to increase the pressure on the balloon. I'm going to just take it and I'm going to squeeze it with my hands to increase the pressure. What's going to happen to the volume of the balloon? And if you said that the volume is going to go down, you're right? If I put more pressure, the volume of the balloon goes down. The volume of the balloon goes down. Okay. If I decrease the pressure, maybe if I pull out, the volume of the balloon goes up. And so we have this counteracting relationship between pressure and volume. More pressure, less volume. Less pressure, more volume. This is pressure on the outside of the container. And that's Boyle's law. That's Boyle, by the way. He came up with this law, and we call it Boyle's law. I don't like naming it after dead white guys, but the curriculum says you have to know Boyle's law, and people refer to it as Boyle's law. So Boyle's law says that pressure is inversely proportional to volume. And inversely proportional has a specific definition in science, and that's that proportionality is linear. So if I have twice the pressure, I'll have half the volume. 3 times the pressure, I'll have 1/3 the volume, and so on and so forth. That's the inverse proportionality. And here's a graph of it. It's a graph of it. P is proportional to 1 over V. So yeah, twice the pressure, half the volume. And you can figure it out with P1V1 equals P2V2. It's kind of like that concentration and volume thing that we had before. But it makes sense with the kinetic theory. If I push in harder, if I have more outside pressure, if there's less volume, they have to work harder. They hit the walls harder, so there's more pressure pushing out. Because the walls are closer, so they're more likely to hit them, so there's more collision, so there's more pressure. That's how we can explain it with the kinetic theory. And that's Boyle's law. It's the pressure-volume relationship. You don't have to memorize it because, you can kind of take it from first terms, from first principles. If to increase the pressure, I have to decrease the volume. To decrease the pressure, I have to increase the volume. Right. The next one is gases and temperature. So you think about this one. This is going to be temperature and volume. What happens if I increase the temperature and keep the volume the same? So this would be a temperature-volume relationship. Temperature-volume relationship. I want to keep the pressure the same, but I want to increase the temperature. So in that case, this would be like if I had this balloon, and it's currently equalized with the air pressure outside, right? The air pressure inside pushing out, the air pressure outside pushing in. If I took it and I heated it up, what would happen to the gas molecules, and what would that do to the volume? So think about that. This is a different dead white guy. This is Charles' law. Charles' law. So what happens if I heat up this balloon? Well, if I heat up this balloon, the gas molecules are going to be moving faster, and they're going to push out more. They're going to push out more. And so the volume will increase. The volume will increase. It's going to stay at the same pressure because it's equalizing the pressure between itself and the environment. So that's Charles' law. Charles's law, another way to say it, because the guy's name was Charles, last name was Charles. Volume is directly proportional to temperature. So this is different. This is increase the temperature, increase the volume. Remember, before it was increase the pressure, decrease the volume. So these actually go up and down together. And it's a direct proportionality. So twice the temperature, twice the volume. 3 times the temperature, 3 times the volume. 4 times the temperature, 4 times the volume. But this is where we run into a problem. We run into a problem here because temperatures in the Celsius scale can go negative. And yet, there's no such thing as a negative volume. I can take this balloon and I can put it in my fridge and it'll still have volume, even though my freezer is at minus 20. Which means that there must be some kind of temperature where this volume will go to 0, according to Charles's law. And that's where we get into our concept of absolute zero. Absolute zero. So if we track different gases at different temperatures and different pressures, and we cool them down and we see what happens to the volume, here's the volume versus the temperature, they all kind of connect. No matter how much gas I have and how much initial pressure I put it in, they all go to 0 volume and 0 pressure at a certain place. And it's down here. It's at minus 273.15 degrees Celsius. This is what we call absolute zero because it's 0 volume. And 0 volume, remember that the volume comes from the movement of particles. So absolute zero is the place where particles will have no energy and all molecule motion will stop. Hence no volume, because the gas won't be moving to make any pressure on the balloon. And that's the name. That's why it's called absolute. It's impossible to go below it. It is the stop. Because you can't have negative motion. It's just motion the other direction. So absolute zero is the coldest possible temperature. And it's from there that we get Charles's law. When we say twice the temperature, we mean twice the temperature from absolute zero. It's an absolute temperature scale. And that's minus 273.15 degrees Celsius is absolute zero. Now that's kind of annoying to always have a minus 273.15 degrees Celsius as our absolute zero. The Celsius scale was developed before we knew about absolute zero. So there's a new scale that was developed. It's called Kelvin. Kelvin, K. 0 Kelvin is that absolute 0 point. 0 Kelvin is absolute zero. So at 0 Kelvin, things have 0 motion. At 1 Kelvin, they have some amount of motion. At 2 Kelvin, they have some amount of motion. And then if you've got double the Kelvin, if you've got like 15 Kelvin versus 30 Kelvin, the 30 Kelvin particles are moving twice as fast. They have twice the energy as the 15 Kelvin molecules. And that's how Kelvin works, twice the particle motion. And to convert, it's actually using the same scale as Celsius, as degrees Celsius. So 1 Kelvin difference is the same as 1 degree Celsius difference. And so like right now it's like 20 degrees outside. That means it's 293 Kelvin, 293.15 Kelvin outside right now. 30 degrees Celsius would be 303 Kelvin and stuff like that. 25 degrees Celsius, which is a very standard chemistry temperature, is 298 Kelvin. You'll see 298 Kelvin show up a lot. Which means that if I wanted to double this balloon's volume, I'd have to double the Kelvin. If it's about 300 Kelvin, I'd have to double that to 600 Kelvin to make this volume go up by a factor of 2. That's 300 degrees Celsius with 600 Kelvin minus 273. It's about 300 degrees Celsius. So we don't see large changes in volume with temperature very often, but that's Kelvin. We have to use Kelvin. One big note, there's no degrees symbol. I see a lot of students write degrees Kelvin. It's not a degrees, it's an absolute, so it doesn't get a degrees. That's just a stupid meme here. Fahrenheit, 0 degrees is cold, 100 degrees is hot, 0 degrees Celsius is pretty cold versus dead. And then in Kelvin, 0 Kelvin is dead. No degrees, 0 is dead. And 100 is still dead because 100 Kelvin is minus 200 degrees Celsius. Minus 173. Right. So that's Charles' law. If we do it in Kelvin instead of Celsius, right, this is Charles' law in Celsius back here, that's in Celsius. Here's Charles' law in Kelvin, and it suddenly makes a lot more sense. We just have to realize that like 0 degrees Celsius is like somewhere here on the chart. So that's Charles' law, and you have an expression you can use if you want. That's just double the temperature, double the volume. It has to be in Kelvin though. Now the last law that we're going to learn as an individual law is the temperature versus pressure law, which the dead white guy that it's named after is called Gay-Lussac. His last name was Gay-Lussac. That's the temperature pressure. That one's probably the easiest one to understand. Right? What happens if I heat up a container of gas, and it's but it's like a rigid container. It's a very solid container, and I heat it up. Well, the particles are going to be moving faster and faster and faster and faster, but it's still rigid. So there's more collisions because the particles are moving faster. So you get more pressure, and eventually it'll burst. This is why, like hairspray cans and stuff, they tell you not to leave it in the heat. This is why, propane tanks have to be shielded and stuff like that. It's a temperature versus pressure thing, and that's this guy's law, Gay-Lussac. That's his name. Again, his last name was a hyphenated, Gay-Lussac. Pressure is, so it says pressure is directly proportional to temperature, just like the volume thing. Twice the temperature in Kelvin is twice the pressure. So, same concept as the volume, but it's on a rigid thing, not a squishy thing. Okay, if it's a rigid container and it can't increase in volume, it'll just increase in pressure. But in order to double the pressure, you have to double the Kelvin. So, if it's 300 Kelvin is kind of normal room temperature, you have to go to 600 Kelvin. You have to go to about 300 degrees Celsius in order to double the pressure of a sealed container. So it's not like this changes in pressure too much in normal experience. That's Gay-Lussac. Here's a graph. Remember, it's in Kelvin. And there's some, ratio you can do, but just remember twice is twice, twice the change is twice. It's all about ratios. That's that. Now we're going to combine these gas laws. So that's our next step here. We're going to do a combined gas law. Oh, we can put this together. We have P1 V1 equals P2 V2. V1 over T1 equals V2 over T2, and P1 over T1 equals P2 over T2. We can put them all together into the combined gas law. And this isn't named after a dead white guy because people got smart enough to realize, it's just call it what it is. It's a combined gas law. So P1 V1 over T1 equals P2 V2 over T2. And so if you know the changes in two of them, you can solve for the change in a third. But all this is really saying is you can combine the gas laws together. If I decrease the volume by a factor of 2 and increase the temperature by a factor of 2, I'm going to get twice the pressure and then from the temperature and then twice the pressure again from the volume. So double the pressure times double the pressure is going to be 4 times the pressure. Or I can cancel it out. If I increase the pressure but decrease the temperature, my volume is going to stay the same. If I increase the pressure but also increase the temperature, my volume is going to stay the same. Stuff like that. I can make it work. That's the combined gas law. We'll do some practice problems with that in class. You'll see it's very, very ratio based. It's very ratio heavy. That's the combined gas law. Last thing to add here is Avogadro. Avogadro has his own gas law. Sometimes it's called Avogadro's law, but it's more often called the Avogadro hypothesis. And because he was working with moles, he said that, here, I'll just move my face up here. He said that equal volumes of gases at the same temperature and pressure have the same number of molecules. This is a really powerful idea. This tells us that we don't care what the gas is. It can be oxygen, hydrogen, carbon dioxide, nitrogen, methane, any gas you want. If we have a certain amount of moles of it at a certain temperature, at a certain pressure, it'll take up the same volume. So whatever gas is in this balloon, it doesn't matter what the gas is. All the math works the same way. It's the same number of moles as long as it's the same temperature, the same pressure, the same volume. That's really, really powerful because it means we don't have to take one of these out, right? We don't care what the element is. We can use these gas laws without even ever knowing the identity of the gas in here. It's very, very cool. So Avogadro's hypothesis is a new thing. It's adding number of moles. If I take this and I put twice as much air in there, twice as many molecules of air in there, it'll double the volume. Makes sense. If I take a rigid container and try to shove double the air in there, double the molecules of air in there, it'll double the pressure instead. If I try that, it'll actually change the temperature too. If I try it on something where, where the temperature can be affected, if I shove double the molecules in, I could also just increase the temperature instead. This is actually the concept behind air conditioning, which is nice. So that comes together to the ideal gas law. Adding in the number of moles makes this law where you can add in the number of moles and you get a constant in any gas. If you take the pressure times the volume and divide it by the temperature times the number of moles, you get a constant. And it's always constant. You can change the volume, and then these will adjust to keep it constant and stuff like that. It's the same. This constant is also the same for all gases because of this Avogadro thing where every gas works the same. And that leads us to the ideal gas law. It's named ideal gas law not because the law is ideal, but because it's trying to predict an ideal gas. A gas with, as we mentioned, point molecules and no attraction or repulsion from itself. That would be an ideal gas. And here's the best statement of it. If we have, I'll move that down. Move that over here, actually. There we go. I'm nice in the corner there. If we have n moles of gas at a given temperature in Kelvin, pressure, and volume, we have this equation. And R is known. R is the same for all gases. It's kind of like Avogadro's number, but it's the same for all gases. If we use the pressure in pascals, the volume in meters cubed, the amount of substance in moles, and the temperature in Kelvin, R comes out to about 8.315. It's actually surprisingly nice that it's like a nice round number without a bunch of zeros in it. It's just 8.315. And that's the value of R. This also works, and I'm going to fix this. If we change the pascals, if we double the pressure but cut the volume by a factor of 2, oh well, that's not working. If we increase the pressure by a factor of 1,000, the pressure would be in kilopascals. If we decrease the volume by a factor of 1,000, which is a liter, like a meter cubed is 1,000 liters, 1 liter. We use kPa and liters. It still works because we've increased the P by 1,000, but we've decreased the V by 1,000. So it works out to the same. So that's PV equals nRT. We can use it to solve all kinds of problems. We're going to see that in tomorrow's lesson because this one's running a little bit long now. We have 4 unknowns and a constant. 4 unknowns and a constant, which means that we can if we know 3 of the things, we can calculate the 4th. So we can figure out V if we know N, T, and P. Remember that R is a constant, 8.315, as long as we're working in kilopascals, liters, and Kelvin, and moles. And you can actually use that, PV equals nRT, you can rearrange it for R, solve it for R, and you get the other gas laws. You get all the other gas laws out of it. It's very, very handy. Everything else will cancel out. So let's say your pressure stays constant. Pressure 1 equals pressure 2. It's gone. It's out of the equation. It reduces to 1. Volume stays the same. If it's a rigid container, take out the volumes. Stuff like that. So that's how that works. Of course, it's not a real gas. In a real gas, there's slight attraction. They do take up a bit of space. But it's good enough for general purposes. The ideal gas law is good enough to estimate for general purposes. If you're interested in physical chemistry, there's little fudge factors that we can add to the ideal gas law. Each gas has its own little tiny fudge factor for, oh, it does actually take up a bit of space. Oh, there is a little bit of attraction to itself and stuff like that. But that's not a grade 11 concept. It's not even a grade 12 concept. That's like analytical chemistry. Maybe second year university, you might learn about that kind of stuff. Now the last piece is it's handy to have standard temperatures and pressures, just so that everyone agrees what kinds of conditions we're going to measure gases in, temperatures and pressures, and these are the standard temperatures and pressures. We usually care more about volumes than the number of moles. So we have when we measure a gas, when we want to give kind of the characteristics, the properties of a gas, typically chemists will measure in one of 2 ways. Either at standard temperature and pressure, which is 0 degrees Celsius, and 100 kPa, kilopascals. So a little bit lower than like standard atmospheric pressure. Or standard ambient temperature and pressure, which is 25 degrees Celsius, which is easier to hit in a lab, right? And your lab's probably about 25 degrees Celsius already, and still 100 kilopascals. So still a little bit lower than your typical pressure, but that's fine. But yeah, those are standardized. It's one of those things like the mole, where it only has power if everybody agrees on what it is. So you'll see STP and SATP a lot. Most things are, I think, measured in STP, and things are starting to get measured more in SATP these days, because I mean, really, 0 Celsius is kind of, it's easy to get because, you know, it's the freezing point of water, but it's kind of arbitrary. So is 25 Celsius, but it's easier to hit in a lab. The last piece here is we take STP and SATP, and I'll move that down. We can actually work out, because we have a temperature and a pressure, we could work out what the relationship between the number of moles and the volume is. And as it turns out, at STP, 1 mole of literally any gas, remember it can be carbon dioxide, hydrogen, nitrogen, oxygen, whatever, any gas, it'll take up 22.4 liters of volume at STP. So that's at 0 degrees Celsius and 100 kilopascals. At SATP, which is 25 degrees Celsius, which is a little closer to normal conditions, it's 24.8 liters of volume for 1 mole of gas. Every mole takes up about 25 liters of volume. So this thing is quite small. There's definitely less than a mole in here, because we're pretty much at standard ambient temperature and pressure here. We're pretty much at 25 degrees Celsius and pretty much at 100 kPa. But this is definitely less than 1 mole of gas. I'd have to be at 25 liters to take up that much. And if you think about it, that's a bit bigger than one of those big jugs, those big blue jugs of water that people buy and put in the water coolers. Those are about 20 liters. So that could be a good reference for a molar volume, for a standard molar volume. Very handy shortcut, because you're basically moles per liter of gas, but it's always 1 liter per 24.8 moles at SATP. Very handy shortcut. We'll be using it a lot in tomorrow's lesson. But for now, that's the end. That's half an hour. We talked about the particle theory of matter. We used it to explain Boyle's law, Charles' law, and Gay-Lussac's law. We talked about how we need absolute zero in order to have a proper correlation to actually have twice the temperature make twice the volume, and twice the temperature make twice the pressure. We need absolute zero. Then we combined those gas laws and made the ideal gas law, and we will be seeing applications of those tomorrow in the last lesson of the course. We'll be solving some problems involving gases. That's it. Thanks for paying attention, and we'll see you guys in class.